So, in the last lecture we saw that if the C star algebra is generated by a single normal operator, then it becomes a commutative C star algebra with identity. The Gelfand transform identifies the operator T with the identity function on the spectrum, that is lambda going to lambda on the spectrum of T. Okay. And then you see how the continuous functions on the spectrum is generated from that particular function, right. Lambda, you will get lambda bar by taking T star, and then polynomials in lambda and lambda bar taking by taking polynomials T in T and T star and so on, and then taking the closure. Okay. So, let us continue with the single operator case. And so, the bispectral theorem 1 by spectral theorem 1. So, that is the first version of the spectral theorem, which gave us a projection valued measure. We have a unique projection valued measure, well, regular, right, regular projection valued measure P. So, we will denote it by P. Well, actually one should say P sub T, but I will not write the subscript T because we have fixed the operator T. Okay. So, P such that T sub f is equal to integral over the spectrum f dp for, well, so you can write f lambda dp lambda if you want, or f. Okay. So, maybe let me write down that as well, because sometimes we write it just so that the variables are clear. Okay. For every f continuous, right. So, for every f continuous, and then we extended it to the bounded function, but let me write just continuous functions for the time being. In particular, the if f is the identity function, that is lambda going to lambda, then T sub f is simply the operator T, right. So, the operator T is sigma integral over sigma T lambda dp lambda. Okay. So, this is the form of the spectral theorem, or the projection valued measure form of the spectral theorem for normal operators. Okay. So, you can write any normal operator in this form, lambda times dp lambda for a unique regular projection valued measure P, of course, which depends on T. If you have a different operator, you will get a different projection valued measure P. Okay. Such that its integral with respect to the identity function on the spectrum, that is lambda going to lambda on the spectrum, is your operator T. Okay. And then one can, so let me, so this would be a slight repetition of what you already know. Okay. Since f going to integral over sigma t f dp, once you have this projection valued measure, we know that this is a star homomorphism and so on, is a star homomorphism. Okay. From, well, initially from continuous functions on sigma to the C star algebra generated by T, which we extended to bounded functions on sigma to bounded operators on the Hilbert space H, right. So, it is a star homomorphism. We get that, yeah, this is something you should realize, that T star goes to lambda bar, right. So, we get that T star can be written as integral over sigma T lambda bar dp lambda, right. So, this is something you have seen in the case of finite dimensional spectral theorem. Okay. So, let us recall that finite dimensional case. If T is, so let us say A is a normal matrix, I can identify, so I can diagonalize A, right. This is the finite dimensional spectral theorem. We diagonalize A and I can write A as, well, using the projections to the eigenspaces, we can write this as summation lambda, let us say p lambda, where lambda coming from spectrum of A, right, eigenvalues of A. So, when I write eigenvalues of A, I am not repeating it. So, p lambda is the projection to the eigenspace corresponding to the eigenvalue lambda. Okay. So, let me write down that P lambda is the orthogonal projection. So, it is a self adjoint projection onto the lambda eigenspace, right. So, if lambda 1, lambda 2 etcetera lambda k are the distinct eigenvalues, I will have sum over lambda 1 sum over 1 to k lambda j p lambda j, right. So, that is what is written here. Okay. So, if A is like this, so in the matrix form A is simply a diagonal matrix with all the eigenvalues on the diagonal, right. What is A star? It would be the diagonal matrix with all the complex conjugate of eigenvalues of A on the diagonal, right. So, in the projection valued measure form, A star is simply summation lambda in the spectrum of A, but I will have lambda bar and p lambda, right, because if I take the star of this, I am going to get that. That is precisely what is written here, right. It is just that we do not have a finite sum anymore, because we have a bounded operator on a Hilbert space, and so you may not even have eigenvalues. So, the summation is replaced with a general integral with respect to a projection valued measure. Okay. So, one should always compare with what you know in the case of finite dimensional spectral theorem, just to see the analog. Okay. So, well, it follows that. So, to continue with whatever we were doing, it follows that. So, this is something which I was saying earlier. It follows that if p lambda lambda bar is a polynomial. So, the polynomial let us write it in terms of summation j equal to k equal to 1 to let us say n c j k lambda j lambda to the j lambda bar to the k, then because we have a star homomorphism and so on, it is t which goes to lambda, right, t star goes to lambda bar, and using whatever we have here and whatever we have here, and the fact that this is a star homomorphism, it immediately follows that p of t star is integral of sigma t of this polynomial with respect to the projection valued measure p, right. Now, if f is a continuous function on sigma t, then there exist polynomials p n converging to f uniformly, right. Then, so, I am essentially doing whatever we did for the algebra for the algebra in the general case earlier. We are restricting everything to the algebra generated by a single operator. Okay. So, we are not proving anything essentially new, but we are sort of specifying everything in the case of a single operator t, which is normal. Okay. So, now if f is a continuous function, then there exist polynomials, right, p n such that p n converges to f uniformly. And so, the integral of p n with respect to this projection valued measure, that so that particular operator has to converge to integral over sigma t f dp, okay, in the operator norm, right, because we are still in the continuous functional calculus case, where we have a star isometric isomorphism, right. So, if p n converges to p uniformly, that is in the norm of continuous functions on sigma t, then the images, right, the Gelfand transform or its inverse images will converge in the operator norm, okay. And this is what we denoted by t sub f, right, in our notation. Okay. In other words, t sub f, if I take this is the operator and I take the Gelfand transform, I should get a continuous function which is f, right, that is what our notation. Okay. So, we will denote it by f t. Okay. So, we will denote this operator So, this is just a notation by f of t, right, that makes sense. If f is a polynomial, then so let us say p lambda lambda bar, then p of t would look like summation wherever there is lambda you replace it with t, wherever there is lambda bar you replace it with t star, right. So, this is a good notation to use. So, we will denote it by f of t. Okay. So, that means f of t is integral over sigma t f lambda dp lambda, right, or simply f dp. Okay, we will use both, right. When f is the identity function, that is f lambda equal to lambda, on the left hand side you should get f t equal to t, right. So, t equal to lambda dp and t square would be lambda square and so on, right. So, the notation is consistent, and this is true for every f which is a continuous function. And then once it is, so once the notation is consistent for continuous function, you can extend it, right. So, we can, so I will not bother about this, we can extend this to all bounded functions as well, right, all bounded functions. That means, the t sub f's are obtained by integrating f against the projection valued measure. The projection valued measure came from the spectral theorem for the normal operator t, right, or the spectral theorem for the C star algebra generated by the normal operator t, right. So, for every if f is a bounded function on sigma, right, which is sigma t, the spectrum of t, then f of t which is t sub f. Okay. So, f of t is defined to be integral over sigma t or sigma f dp. Okay. This is essentially a change of notation, there is nothing new here, because we have done this for the algebras we looked at earlier. Okay. But let me sum up. So, to sum up, we get, so let me write this as a theorem, because we have been writing the theorem for algebra of operators. Now, we are writing it for a algebra generated by a single operator, right. So, theorem, let T be a bounded operator on a Hilbert space which is normal, be normal. Okay. Then there exists a unique star homomorphism, So, I will go directly to bounded functions instead of stopping at continuous functions. From bounded functions on sigma t, right. So, remember the normal B stands for bounded functions, script will stand for Borel sigma algebra, right. So, bounded functions on sigma t into the bounded operators on the Hilbert space H, right. Well, what is the homomorphism? That is f going to, so if I take a function f, it is f of t, right. So, that is the homomorphism. F of t is given by a projection valued measure, I will write it down later, f of t for f in such that, so the homomorphism is set up so that f t is equal to t if f of lambda equal to lambda, right. So, if f is the identity function lambda going to lambda, then the corresponding operator I get is the operator t, okay, comma f and t converges to f t in the strong operator topology, in the strong operator topology, provided f n converges to f in the f n converges to f pointwise and boundedly, right. So, we proved this, right. So, f n converges to f pointwise and boundedly, right. Well, how did this happen? This happened because of the second version of the spectral theorem and all that, we have already done that. Moreover, so maybe just to complete, moreover, there exists unique regular projection valued measure, P such that f of t is equal to integral over sigma t f dp. Okay. So, most of this is just repetition of what we have done earlier, but this is the spectral theorem for a normal operator, but this is the projection valued measure version. Okay. So, this is a, you can think of this as a generalization of what you have seen in the case of finite dimensional normal matrices, where you can write your operator A as summation lambda p sub lambda, where p sub lambdas are projection to the lambda eigenspace, and you replace the summation by an appropriate integral, but then you are integrating against a projection valued measure. And you can see that if you assume that your Hilbert space is finite dimensional, then this reduces to the spectral theorem you already know. Okay. So, let us continue. So, via spectral theorem 2, So, spectral theorem 2 identified the algebra A with multiplication operators, right. We can realize T as a multiplication operator. Okay. So, what is that? First consider the case. So, let us look at the cyclic case. Okay. So, first look at the cyclic case. Okay. So, what is a cyclic case? That means there is a vector v such that if I apply t and powers of t, I will get a dense subspace, right. So, that is well, I should take t and t star, right, because it is a normal case, normal operator, t and t star can be different. So, that is p of t star acting on v, okay, that is okay. So, maybe I should say there exists a vector, there exists v in H such that p is a polynomial, okay, contained in H is dense. Okay. So, well, this is equivalent to what we had written earlier, right. If I had an algebra A, then I look at A acting on V. Here I am only looking at the polynomials, but when I take the closure I am going to get all of A, right, the C star algebra generated by T and T star, and then I take the closure. Okay. So, these two are same. Well, or so maybe it is better to write that, because we had written down that earlier, right, or A V closure equal to H, right, where A is the C star algebra generated by T, right, C star algebra generated by T. Okay. Now, so this is a cyclic case. So, if I like we did in the earlier case, let mu be equal to mu v v, right, that is the measure we had defined. Then we showed that any S in A. So, you look at L2 of mu, and there is a map from the Hilbert space H to L2 of mu, which was unitary, which was essentially the map SV going to the Gelfand transform of S, right. So, SV was going to Gelfand transform of F, right. This was the this was the unitary which took the Hilbert space H to L2 of mu. So, after composing with this unitary, we showed that any S in A can be realized as a multiplication operator, right, the multiplication by S hat, the Gelfand transform F, right. So, we showed that any S can be realized as multiplication by multiplication by S hat on L2 of mu, right. This was the multiplication form of the spectral theorem, right. In particular, what happens to the operator T? Remember, the A is generated, the C-star algebra A is generated by the single operator, normal operator T, right. So, in particular, so this is just writing the multiplication form of the spectral theorem for the normal operator T. Okay. So, in particular, the given normal operator T can be realized as multiplication by let us say m lambda. What is m lambda? M lambda is the multiplication by lambda, right. So, m lambda of g equal to, well, I should say at lambda, right. So, m lambda at g at lambda equal to lambda times g lambda, right. So, you take any g in L2 of mu and multiply it with lambda, right, lambda times g lambda, that is, so g going to lambda times g, right, that is your operator, because T hat is just the identity function lambda, right. So, any normal operator, if it has a cyclic vector, then can be realized as simply multiplication by lambda on a, well, actually if you take the cyclic vector to have norm 1, it is a probability measure, right. So, these are your normal models of normal operators with cyclic vectors. So, can be realized as m lambda on L2 of mu. In the general case, what do? You look at the cyclic subspace generated by one vector and then take the direct sum, right. So, in the general case, take the direct sum. So, what did we prove? So, just to sum it up like we did earlier in the projection valued case. So, we proved the, right, to sum up, so let T be a normal operator, be normal, then there exists a measure semi-finite measure space, So, instead of writing the spectral theorem for the algebra, I am just writing it for a single normal operator, right. So, there exists a semi-finite measure space omega f mu. All these spaces you saw earlier, omega can be taken as several copies of the spectrum of T, right. So, recall that this is copies of disjoint union of copies of sigma of T, right. Sigma of A is identified with sigma of T, because A is generated by T, right, and mu was finite restricted to each of these copies, and the multiplication is simply the Gelfand transform, but the Gelfand transform of T is the identity function lambda going to lambda. So, it is just multiplication by lambda on this space, semi finite measure space omega f mu such that T is unitarily equivalent to m on L2 of omega f mu, where, so let me not write m lambda, let me just write m, where m of phi at lambda equal to lambda times phi lambda for phi in L2 of omega f mu. Okay. Of course, if H is a separable Hilbert space, you can take your measure mu to be a finite measure, right. So, all the normal operators. So, this is how you think of spectral theorem, all the normal operators are precisely multiplication by z or multiplication by lambda on an L2 space. And if your Hilbert space is separable, you can think of this as a finite or a probability measure in fact. So, model normal operators are precisely multiplication by lambda or multiplication by z on some subset of the some compact subset of the complex plane with respect to on an L2 space with respect to a probability measure, right. These are your normal operators, and essentially everything can be deduced from this this form of the normal the spectral theorem. But remember that depending on how you take these cyclic subspaces and so on, there is some loss of uniqueness, right. So, there is no we may be able to realize the operator as a multiplication operator on some other L2 space, right, with some other measure. What is the relation between these two measures, how are they related to each other is a question which is related to what is known as the multiplicity theory. We will try to see some of that in the later classes. So, we will see that these measures there is not much room, you can't take any arbitrary measure. If I have one representation like this, any other representation will give me a measure which is mutually absolutely continuous with respect to the given measure. Okay. So, there is a measure class associated with the normal operator. So, given this normal operator T, I can think of it as a multiplication on some L2 space with respect to let us say probability measure in the separable case. So, we will stick to the separable case. Okay. So, Hilbert space is always assumed to be separable. In that case, the normal operator can be viewed as multiplication by lambda or multiplication by z on the L2 space on the spectrum, right. The spectrum is a compact subset of the complex plane with respect to a probability measure. The probability measure we come up with is not necessarily unique. You can have a measure class, that means any other representation is going to give me a measure which is mutually absolutely continuous with respect to the original one. So, instead of one measure you have a measure class. Okay. So, the measure class is going to be unique. So, we will see some of this at later classes. Okay. So, let me stop with one exercise. So, let mu be a sigma finite measure on some space X, right, with a sigma algebra F. Okay. So, X is a set, F is a script F is a subset sigma algebra of subsets of X. Okay. Let phi from X to C be measurable. So, it is a measurable function bounded. Okay. So, bounded measurable function okay. And define T from, so this is a measure, this is the operator you already know, L2 of mu to L2 of mu by multiplication by phi, right. So, T of f equal to phi times f. So, this is m phi, right, multiplication by phi for f in L2 of mu. Okay. Then the spectrum of T, well, what is that? The spectrum of T is the essential range of phi, with respect to mu, of course, right. So, I can after redefining phi on a set of measure 0, on a set of mu measure 0, we may assume that range of phi is actually equal to the spectrum, right. Essential range is what is phi is the spectrum actually, but you redefine on a set of measure 0. So, if you redefine phi on a set of measure 0, the operator is not going to change, right, because T f equal to phi f, and if I change phi different representative of phi f and the new representative times f will be the same functions as functions on L2. Now, if you look at this operator, so the operator T is normal, right, because T star is multiplication by phi bar and T star commute, right. So, question is what is the spectral theorem for this? Of course, this is already in the multiplication operator form, but the theorem we have written says that if I have a normal operator, it is going to be multiplication by z or multiplication by lambda, right. So, you want to write your operator as multiplication by lambda. Okay. So, for that define nu on the Borel sigma algebra of the spectrum of T. So, this is the Borel sigma algebra. Okay. By so nu of E equal to mu of phi inverse E. Okay. So, I have this measure. So, I have x, f and mu. I have this function phi which is going here and its range is the spectrum, right. So, here I have the Borel sigma algebra and I am defining this measure nu by pulling it back, right. So, mu of phi inverse. Okay. So, prove that. So, once you do this, prove that. So, on the spectrum I am saying the operator T looks like multiplication by lambda. So, prove that T is unitarily equivalent to m, okay, where so m on L2 of the other measure nu, where m g let us say at z equal to z times g z, right, or lambda times d lambda, whatever way you want to write. So, I am realizing. So, I will stop here. We are realizing this normal operator, which is the simplest of the normal operators, which is multiplication by a bounded function by changing the measure, right. So, you change the measure appropriately, you can identify it as multiplication by z on an appropriate L2 space on the spectrum. Okay. Alright. So, we will stop here. We will continue with the study of the single normal operator and then we will restrict ourselves to self adjoint operators later on, probably from the next lecture onwards, and study it in much more detail. Whatever we do with the self adjoint operators, one can actually do with normal operators as well, just that it gets a bit more complicated, that is all. Okay. So, we will stop here.